Let's say you're studying a map, looking for a certain location along the equator. What information do you need to find it? Just one number, the longitude, which tells you how far east or west you have to go. You can think of your search as an algebra problem solved for one variable, just like the other problems we've worked on in other modules so far. In every case, we've been looking for a definite point along the real number line. If the answer is 1.5, for example, we can actually draw the number line to help us out. Even in more complex formulas, we've always treated just one letter as the variable. But now, suppose that instead of looking for one point on the equator, you're looking for a tiny island somewhere in the Pacific Ocean. Can you pinpoint that with just one number? No, it's not on the equator this time, so you need two numbers. One to tell you how far to sail east or west, another to tell you how far to sail north or south. That gives us a problem with two variables. Problems with two variables must be approached in a different way, and that's what we're going to look at now. First, we need a useful tool like our map. Simple enough. We'll use two number lines, one going east and west and another going north and south. We will arrange them so that they cross where each number line is 0. That 0 point will be given a special name now, the origin. The horizontal or east-west line is called the x-axis for short, and the vertical or north-south line is the y-axis. And the whole picture is called the Cartesian plane or coordinate plane. That's a fancy name for a big flat field or surface. The x and y axes divide the surface into 4 parts. These 4 sections have names too. They're called quadrants, and they're numbered from 1 to 4 counterclockwise. We've sailed out of the Pacific Ocean now and into the Cartesian plane. But if there's an island out there, or any other kind of point with a location that we want to identify, it's an easy task. All we have to do is find two numbers. We extend an imaginary line from our point to the x-axis. We find our first number where the line crosses the x-axis. A line extended from our point to the y-axis gives us our second number. Then we write down these two numbers in proper order. Which comes first? The number of the x-coordinate. The order follows the alphabet, x, then y. The point we're trying to locate here has an x-coordinate of 4. It's opposite 4 on the x-axis. On the y, or vertical axis, it's opposite 3. Its y-coordinate is 3. When we write coordinates, x comes before y, and we put them into parentheses, separated by a comma. X is 4, y is 3, so our first point, our first lost island, is found at coordinates 4, 3. It's all pretty straightforward. If you remember, x is horizontal or east-west, and that number comes first. Y is vertical or north-south, and it comes second. And the two numbers are written in brackets with a comma in between. That's all you need. It's just that simple. So far we've learned to do two things, which are really just two sides of the same coin. If we're given the location of a point on the Cartesian plane, we can determine its x and y coordinates. Or, working in the other direction, if we are given a set of coordinates, we can plot the exact location of the point on the coordinate plane. Keep in mind that in every case we've been dealing with one point at a time. We have two coordinates, x and y, which locate that point, but those two numbers describe the location of only one point. Got it? Good. Let's do some practice. Here are 2 points. Pause the program while you write the coordinates for each. When you are done, click play again, and we'll check your answers. The red point is opposite 4 on the x-axis. On the y-axis, it's opposite -2. So the coordinates of this point are 4, -2. Similarly, the orange point is opposite -1 on the x-axis and -3 on the y-axis, giving it coordinates of -1, -3. Now try the process in reverse. Start with coordinates and plot the points. Draw yourself a set of x and y axes, then plot 2 points using these 2 sets of coordinates. Pause the program while you work. When you're done, click play and we'll compare answers. My coordinate plane comes out looking like this, with the first point out there on the upper left. The second point, for 0, has a y-coordinate of 0. It lies right on the line of the x-axis because that's where y is equal to 0. Now let's see how we can use these ideas to draw pictures of equations. With only one variable, we could show the solution of an equation like this. It's just one point on a number line. But with 2 variables, we need a different way to show the solution. In this example, we want to show all the values for x and y that will make this a true statement. What happens if we use our coordinate plane to plot the pairs of values? A plane that just happens to have a horizontal line to plot one variable and a vertical line to plot the second variable. Let's try some number pairs. X equals 1 and y equals 1 is certainly a correct solution. Substitute to prove that it works. So we go 1 for x on the x-axis and 1 for y on the y-axis and plot our point at 1, 1. Are these the only numbers that add up to 2? No. This problem has more than one point that will work. Here are 3 more points with coordinates in which the value of x plus y is 2. All of these points are correct solutions, so we draw all of them, and something magic happens. The points begin to form a pattern which suggests that as long as we keep on plotting points for x plus y equals 2, the points will all fall on a perfectly straight line running across our coordinate plane. We have just drawn a graph of the equation x plus y equals 2 and learned why it's called a linear equation. But how can we be sure? Couldn't there be a little bump in our line somewhere between 2 of the points? To answer the question properly, you really need calculus. But even without it, we can find an answer. 2 ways. Consider the point right at the top of that proposed bump. What are its x and y coordinates? X is 1/2, y is 3.5. Will x plus y equal 2? No way. The point does not belong on our line plotting the correct solutions at all. All right then, if the x-coordinate is 1/2, then what will the y-coordinate be? That's the kind of problem that algebra is designed to handle. We know that x plus y equals 2, and we know that the x-coordinate is 1/2. Solving for y tells us that y equals 1.5 or 3/2. If you had any problems with these steps, be sure to review the module on how to solve linear equations. It's absolutely basic. So now we know that if the x-coordinate is 1/2, the y-coordinate must be 3/2. Those coordinates indicate, once again, a point right on our straight line. Our let's give it a try bump just won't work. But algebra does work. For any x, we can find the corresponding y by substitution in our equation. Now we can state the result of our investigation. If we take a linear or first-degree equation and graph it, we'll always get a straight line. That means we can easily graph the straight line for any linear equation we like. We just have to calculate a couple of points that satisfy the equation. Then we use those 2 points to define a straight line. Let's try 2x plus 3y equals 8, following these steps. We pick a value for x. Let's say x is 1. By substituting, we find that y equals 2. That gives us the point 1, 2. We do it again for x equals 4. and we get the point 4, 0. Just to be sure, we can find one more point. This time, x will equal 0. And our point is 0, 8/3. We graph our 3 points into the coordinate plane, where they look like this. And just as we predicted, they all fall along a single straight line that continues outward in both directions forever, because that's what you get when you graph a linear equation. Did we actually need all 3 of those points to get our line, our graph? No, we didn't. 2 points are enough to give us the line, as long as they're the right 2 points. But if we made a mistake, a 3rd point will make it obvious, so 3 are safer than 2. I know I sometimes make mistakes. How about you? See if you can do this one. 3 points, no mistakes. Pause the program while you pick your own points and join them up with a straight line. Click play again as soon as you have your graph. We probably didn't choose the same points, but our 2 graphs should look the same. Both our lines will pass through all correct points, just as long as the points each of us picked were among the correct ones. Here are some points that worked. Are they on the line that you graphed? No matter what points were chosen, we should both end up with a line looking like this. And remember, this line just keeps going forever. This is a new kind of problem, and it deserves some practice. Do it right away with some more examples from your textbook, and then we'll see how to use these graphs to solve problems in the module called Equations of Lines and Slope. But right now, the important thing is to get ready by doing some more problems of the same kind. Be sure you master them right away. They're not hard, but it's a skill you will need again.